Problem 6 is the other kind of dilation of a line. So here we have a line, and it's telling me it is dilated. So when you see those buzzwords, dilation of a line, as I was talking about in problem 5, it could be one of two ways. It could be about the origin, which when I read this, yeah, okay, I got a scale factor of 2. But here they're telling me it's centered, it's not at the origin, right? It's not at 0, 0. This is that other kind of problem. This is going to be dilated about a point somewhere else. And for the regions, it's always going to be on the line. And you need to verify that that's a part of the process. Because once you verify that this point is on the line, the answer is very easy. But let's talk about how you verify that the point is on the line. We're not going to do the origin method, which we covered in 5. It's a lot more involved. Well, a point is a collection of an x and a y value. So I can see, and let me color code this, x, which is 3, and y, which is 8. So when I write out this equation, y equals 3x minus 1, I can check if this point, 3, 8, I can check if that belongs to my line by substituting in. I know my x value is supposed to be 3. So let's substitute that. Wherever I see an x, I'm going to put a 3. So that's multiplication, so that's really times 3. Wherever I see a y, I'm supposed to put this 8. So I'm going to erase that 8, and I'm going to substitute in 8. Now I'm going to use the order of operations to simplify. So nothing to do on the left side, I just bring that down. I can tell you 3 times 3 is 9, and then we minus 1. Still simplifying, I see that 8, and 9 minus 1 is 8. So the fact that I get something true, that means that the point belongs to the line, or in other words, it's on the line. And when that happens, when your point of dilation is on the line, nothing happens. The line stays exactly the same. And the reason why this is, you can imagine you have a line, okay? Let's call that y equals 3x minus 1. And when you plot this point, let's assume it's there, 3, 8. That point of dilation, because it's on the line, it kind of holds it down. It's like if you put your finger like on it. I'm terrible with hands. Okay, it's like you put your finger on it and then you stretch the ends out. That line cannot go up. It cannot go down. Sure, it's going to extend out further, but lines go on infinitely. That line is going to stay put because that point is pinning it down. So your answer, once you verify that the point of dilation is literally on the line, your answer is the equation of that line. It's the same line. So your answer is literally y equals 3x minus 1. Exactly what they told us from the start. Nothing changes. So if you buy that method, great. If you want to see it written out for you, I've graphed out the line y equals 3x minus 1. The next thing we need to do is plot the point 3, 8. So I go over 3 in the x and up 8, and you can see, boom, that point is in fact on our line. And if I go to, let me color this line line green, there we go. If I dilate this line about that point, It doesn't matter what the scale factor is. I mean, they told us it was 2. That's really irrelevant. It won't matter, but I'll call it 2. Um, and when we do that, you can see their equations are literally the same thing. They are the same. And I'm going to color the new line red so you can see they lie on top of each other. If I make that line a little bit thicker, you can see the green one's right underneath it. And those lines are the same. They stay put. And that's all because that point of dilation is pinning down that line. It can't get further away from it. The distance to the point of dilation is 0. So no matter how much I multiply that distance, I'm still at a distance of 0 from the point of dilation. That's why the line can't get further away, as in versus the other problem where you can look at that. We were a distance of 1 away, so when we dilate by 4, it got 4 away. But I'll see you in the next one.